So there are 4 ways to activate an alcohol. Basically, all we're talking about is turning it into a good leaving group so we can substitute it. We want to get rid of this OH. We want to turn it into a good leaving group so we can put something else there. We want to substitute this. A lot of times these take place with primary and secondary alcohols. Right? If you're going to do an SN2 mechanism, you have to have primary or secondary. You cannot make a carbocation with a primary alcohol either. Right? So this first one, you'll notice here H2SO4, which could be just written as H+, and then they added in Na plus Br minus. The first step, what do we do here? We're just doing a protonation. Protonation. What did that do? That made this alcohol a better leaving group, right? Now it has a plus charge, it's a better leaving group. The bromine that you added as a reagent down here then can do an SN2 reaction. Because this is a primary alcohol, right, primary OH, do we need to worry about SN2? Or do we need to worry about inversion? Nope, because it's not an asymmetric center. And so then we can get that final bromine net replacement. So a protonation, SN2, and we get the bromine there. The other thing you can do, so instead of using HCl, but make that first one a little more complicated, what you can do is HCl, use this zinc chloride in HCl. And it's very similar to another one we're going to talk about next. Right? But you can imagine this zinc having 2 chlorides on it. And essentially you do an SN2 here to kick out one of the chlorides. Like zinc's a metal, so it's big. You do SN2s on it. What have you done here? You've essentially made your alcohol a really good leaving group again. Right? Your alcohol a really good leaving group again. I would argue there should not be a minus charge there. Actually, there can't be because you need a balanced charge. And if there's a plus charge here and the chlorine's a minus, that's where that came from. So the chlorine comes back around that you lost when it got kicked out. We do an SN2 and get to this type of product. I'm not worried about the inorganic species that you create. So don't worry, like how am I supposed to know whether it's zinc or this? Or down here, they're like, this is how your catalyst gets regenerated. I'm not worried about that. I want you to be able to do these 2 steps. Right? I'm not worried about what happens with this or this or how this all happens. If you want to know about it, I can tell you about it, but that's not what the key point is here. The key point is these are ways to take strong acids, HBr, or things like that, or zinc chloride, and use them to turn an alcohol into a bromine or a chlorine. That's it. All right. Secondary alcohol, it's strong acid. We're going to protonate to turn this alcohol into a good leaving group like water. Because it's a secondary alcohol, we're not going to do an SN2. We're actually going to do the leaving group's going to leave. We're going to make a carbocation, a secondary carbocation. Anytime you make a carbocation, you want to try to do a rearrangement to make a more stable carbocation. In this case, we can do a hydride shift, rearrangement. That goes from a secondary to a tertiary carbocation, at which point the bromine can now come in and add in, and we get the tertiary alkyl halide. The second way to activate alcohols is with PCl3, PBr3, but the one you really kind of focus on is PBr3 is kind of the classic one. So this is a way to use a different reagent that is not a strong acid. So strong acids can react with alkenes or other things. This reagent is a little more selective for alcohol, so it's nice to use that to turn an alcohol into a alkyl halide or alkyl bromide. How does this mechanism work? Again, these are also for primary or secondary alcohols, and I'll talk about that in the review as well, so you can write that in there. Most of these things are for primary or secondary alcohols. It's hard to do substitutions on a tertiary alcohol, right? Because you can't do SN2. It's too sterically bulky. So this mechanism involves 2 SN2 reactions. The first one, a basic example is shown here. This is kind of telling you where things are going, right? You turn this alcohol into a bromide. Notice there's no rearrangements. There's no carbocations in this one. Carbocations are not possible, right, at all. So PBr3 does not make carbocations. The strong acids, the HBRs and the zinc chlorides, those do. No carbocations here. Say it with me. No carbocations. So no rearrangements with this. Right, it's another reason why it's a nice reagent. Not worried about rearrangements. Rearrangements can be a pain. Some folks asked about What's the phosphorus byproduct? This is what it is. It's kind of this resonance form of this. Don't worry about that. This would get washed in the aqueous layer. But there it is for you if you want to see it. So what happens in the first step? Our nucleophile reacts with our electrophilic phosphorus. Does an SN2, right? An SN2 kicks out a bromine. What we've effectively done, we've turned this alcohol, which wasn't a good leaving group, now into a good leaving group. That's the theme. We're just going to keep doing that. Taking this alcohol, make it a good leaving group. So now we've made it a good leaving group. In the second step, we take what we've made a good leaving group now, and we do another SN2 with the bromine that we kicked out in the first step. Do another SN2, and we get our alkyl halide product. And I'm not so worried about this reacting or how you to know that it does, but it does give you extra bromines, right? So each PBr3 has the potential to give you 3 bromines. But I'm worried about these first 2 steps, these first 2 SN2s. The thing you need to remember, though, this is a primary alcohol, right? This is a primary alcohol. If it was a secondary alcohol, and it was an asymmetric center, a chiral center, you need to worry about inversion, right? Inversion in this step. Right, that SN2 thing. Where if this was R, after inversion it becomes S. If this was S, after inversion, after SN2 it becomes R. So what are the things to remember with phosphorus tribromide, which is just PBr3? Is stereospecific. All that means is if you have a chiral secondary alcohol, you're going to do inversion. Right, you're going to do inversion. There are no carbocation rearrangements, so no carbocations, and you don't have to worry about elimination. So it's only doing substitution. So it only works with primary and secondary alcohols, and it's only doing substitutions. So those are 4 things to think about. You'll do inversion if it's chiral center. It has to be secondary, though. No carbocations, no eliminations. So the last 2 are a little more specialty reagents. They use something called thionyl chloride. And what they can do is invert or retain the stereochemistry of a secondary alcohol. You got to think about the mechanism here. So if you look at here's the whole net reaction. Again, we're starting with an alcohol. So this SOCl2 must be somehow activating the alcohol to make it a better leaving group. The alcohol gets replaced with a chlorine. Well, that makes sense. There's SOCl2. We also make HCl and this SO2. SO2 is a gas, and that's going to help drive this reaction forward. Right? Le Chatelier's principle, if one of the products is a gas and it bubbles out of solution, is it coming back in to go revert back to starting materials? No. Unless you have a closed system, which would be dangerous. Right? So what else happens here? So there's your net reaction. If we start out with a secondary alcohol that has a stereocenter, right? Here's one that's an S stereocenter. What happens here is it becomes, when the chlorine adds, it goes from S to R. We get inversion. Right? That means there must have been an SN2 reaction taking place. There must have been an SO2 reaction taking place. There's the gas that helps drive the reaction. Here's pyridine, and we'll talk about pyridine in a second, and the role that plays in helping drive this reaction too. All right, mechanism. Yes, sulfur has an expanded octet, but as far as we're looking at it here, actually it doesn't. Right? So don't worry about this lone pair of the sulfur. Don't worry about it. Just treat this like it's a ketone, right? Treat it like, right, this oxygen reacts with the sulfur. That's electrophilic because it's bonded to 2 chlorines and an oxygen. We do the addition, right? This is an addition step. You add in. What did we do? We just made a tetrahedral intermediate. What do we ask ourselves when we make a tetrahedral intermediate? Do I have a good leaving group? Is chlorine a good leaving group? Oh yeah, it's a great leaving group. Right, we do the elimination. Now the difference here is this pyridine's floating around, basically trying to help us move this reaction along. And it could react, like I said, it could react here or it could react later. I like to show it reacting later, personally. I think it just makes more sense that way for me to see it. But you could do it this way. It's not a big deal. So now we've made the pyridine with the plus charge, and there's still that other Cl- floating around, right? And the trick here with this one is this doesn't crash out a solution. Now it can, but we have a solution for that too. Notice at the end we make a Cl minus, right? So to make this reaction go, we just need one of these to get back around to do this step. So let's take a look. Okay, so we did a deprotonation, right? Now our original Cl minus that we kicked out, comes back around and does an SN2 reaction, right? Because this is a pretty good leaving group. You can imagine this oxygen is being pulled by the chlorine, right? It's a pretty good leaving group. It's being pulled that way. When it does that SN2, we do inversion, right? So if it was S, now it becomes R. Now this last step is where how do we make the gas and how do we recreate a Cl minus, right? Because we're going to need more Cl minuses to do our SN2s. So with thionyl chloride, SOCl2, this last step is another, look at, it's just an elimination. We made a new pi bond, right? And we kicked out and lost another Cl minus, which then can help us come back for the next molecule of alcohol and come back around and keep reacting and do another SN2. So what do we have so far? We have strong acids, HBr, that can make a carbocation. Those rearrange. That was the first way we learned how to activate alcohols. The second way was PBr3. Works with primary and secondary alcohols, no rearrangements, no carbocations, does an SN2. The next one we learned was SOCl2, which was nice. It took an alcohol and made it to a chlorine, but it did inversion, right? So if something was S, it went to R. What if you wanted to stay S? That reagent is this, these alkyl sulfonates. This activation of alcohols allows you to essentially stop at the point where you made the alcohol activated. And then you can add any nucleophile you want. That's the nice part about this. So the other ones, right? HBr makes carbocations. That's a mess, rearrangements. PBr3, SOCl2 naturally just do inversion, right? And you have no way to stop it. These tosylates, they're called, or mesylates. What's nice about these is they don't do inversion. They just make the alcohol activated, and then you can decide which nucleophile you want to add in. You're not stuck using bromine or chlorine, right? So that's the net thing that happens here. If you had wedged, if you're R, you stay R, and then you can add any nucleophile you want. That's the big difference. So these are just showing these names. I'm not going to ask you to know these names. The biggest idea here, why are these good leaving groups? So the one group, the Thionyl Chloride, the SOCl2, was a good one because that made a gas and that drove the reaction, right? These are good leaving groups, right, because of resonance, right? If this group leaves, right, if you break this bond right here, you get O minus, and that can do lots of different resonance. That makes things a stable leaving group, right? Resonance stabilizes things. So these are a couple different places that, I'm not asking you to know those. What's the mechanism look like? Now we have an expanded octet sulfur, but again, it's going to react the same way. This oxygen reacts with the sulfur because it's bound to a chlorine and oxygen. It's very electrophilic. So we do an addition, right? We do an addition. And of course, this isn't a tetrahedral intermediate, right? But you get the idea. It's a similar type thing. Can you do an elimination? Yes, you can. So you do the elimination, right? So that's an elimination that kicks out Cl minus right there. Pyridine comes back in here again, right? Pyridine comes back in here again and does that deprotonation. Deprotonation. And the difference here is this. This crashes out. This becomes a solid. Right? In this reaction, when the pyridine deprotonates and you have that Cl minus around, this actually comes out of solution. You literally see white powder on the bottom of your flask, this salt. And what does that do? That stops, can this chloride then react if it's a solid? If this is in solution, can this Cl minus react? Well, no, right? It's the same idea of like the gas. Once it's out of solution, it's done, right? Whether it's a gas or a solid. So that's what makes this stop here at this point. Then once you have this, then you can do step 2 and add in any nucleophile you want and do inversion. The final thing that's just review from, hopefully from first semester, is essentially these E1 type eliminations. All right, this is an E1 type elimination where you have really strong acids, a tertiary OH or a secondary OH, but you don't have a very good nucleophile around, right? So H3PO5, any of those things like that where you don't have a Br minus floating around, that's right, you're going to get E1, right? Not SN1, E1. So there are a couple sampling problems like this, right? So make sure you remember those E1 principles. And you know, like this is a great example, Zaitsev's rule, right? The more substituted alkene, di-substituted versus monosubstituted, and the E alkene versus the Z alkene, as in Z same side, the E is more stable because things are farther away from each other. All right? Again, up here, Zaitsev's rule, tri-substituted alkene versus a di-substituted alkene. So make sure you know those dehydration of alcohols. There's a couple sampling problems like that.